In today's lesson, we're going to be thinking about bond energies and energy changes, and we're going to be calculating the energy change in a reaction. So the first question is, what do I mean by the energy change in a reaction? So far in this topic on energy and reactions, we've been thinking about exothermic and endothermic reactions. And we've been drawing reaction profiles for those. Okay, so if I draw out a quick profile diagram, so this would be the progress of the reaction, and this would be the energy. And let's say we have an exothermic reaction, so the reactants would be up here, and the products would be lower in energy, as that's the definition of an exothermic reaction. And the reaction profile would look something like that. Okay, and on here we can label a couple of other things. So we can say that this distance here, so this upwards distance here from the reactants to the top of the curve, that is your activation energy. Remember, that's the energy you need to get the reaction started. And then the difference between the reactants and the products, so going from the level of the reactants exactly down to the level of the products exactly, that is your overall energy change. And because it's a negative number, because we're going down, we know that it's an exothermic reaction. Okay, so we know that here this is going to be less than 0, therefore exothermic, therefore energy is transferred from the reaction to the surroundings, and we can therefore know what will happen to the temperature. So the temperature will do what? Yeah, it will increase because we're measuring the temperature of the surroundings. Okay, and today what we're going to do is, because we know all this now already, we're going to be calculating this, the overall energy change. That's what today's lesson is about, how to calculate this. Okay, because in the examples that you've done in previous lessons and in homeworks, I've usually given you that number and then you draw the reaction profile, or I give you the number and you tell me if it's exothermic or endothermic. But today we're going to be working that out. Okay, so step number 1, we need to think first, before we even get to working it out, about something called a bond energy. So let's imagine that we have some chlorine gas. Okay, so we've got some chlorine gas. And you know that chlorine gas is Cl2. Okay, and it's a non-metal, so it's going to be covalently bonded. And what that means is that we can draw it out like this. Okay, so I've got one chlorine atom, I've got my second chlorine atom, and in between them is a covalent bond. And I've been telling you that these covalent bonds are very strong. But what does that mean? Well, now I'm going to give you a number, right? And that number is 243 kilojoules per mole. And this number is the energy required to break 1 mole of Cl-Cl bonds. Okay? Because of course, the chlorine is bonded to the chlorine. So if I want to separate these two chlorines from each other, I need to put energy in. Okay? because I'm going to be pulling them apart, and I'm using that energy to pull them apart. So this energy here is used to pull those atoms apart from each other and break the bond. So we can write this out as a kind of equation. So we can say that if I have 1 mole of Cl2 molecules, and I want to break all the bonds, so all 6.02 times 10 to the 23 bonds, okay, I'm going to get, if I've got 1 mole of Cl2 molecules and I break all the bonds, I'm going to end up with 2 moles of Cl atoms. Okay, you'll remember because in 1 molecule of chlorine, I've got 2 chlorine atoms. So in 1 mole of chlorine molecules, I must have 2 moles of chlorine atoms. And in order to do that, I need to put in 243 kilojoules of energy. Okay, energy put in. And it's really important that you know that it's energy that's put in. Okay, because you're breaking something. So if I were to give you maybe a chain and asked you to break it, so break the links in the chain, like break the bonds between each link, you would need to use energy in order to do that. So we're putting energy in. So that means that we can now think about it in terms of, is it an exothermic process or an endothermic process? Well, if we put energy in, all right, the energy is going to increase. Energy increases, which means that it is an endothermic process. Okay, so this is, we should make this clear, so at the moment we're talking about bond breaking. All right, so in order to break 1 mole of these chlorine-chlorine bonds, we need to put in 243 kilojoules of energy, and then we get our atoms out at the end. Okay, now that's not all that this number here means. It also means something else. All right, it also means if I'm doing bond making. All right, so I can also define it as 243 kilojoules per mole is the energy released when 1 mole of Cl-Cl bonds are made. Okay, now that shouldn't surprise you because when I broke the bonds, I had to put energy in, whereas now I'm making the bonds, so energy is released. So it's the opposite way round. Okay, so if I have 2 moles of Cl atoms, and I use that to make 1 mole of Cl2 molecules, then I will get out 243 kilojoules. All right, because I'm making 1 mole and it's 243 kilojoules per mole. So energy is released from the reaction, which means that the amount of energy in the reaction is decreasing. Which means that it is an exothermic process. Okay, so at this point it's really important that you know that when we break a bond, we have to put energy in, and that's an endothermic process, and when we make a bond, energy is released, and that's an exothermic process. Okay, in fact, if we wanted to, we could even think about it like this. So we could have our reactants here and our products here. Okay, this is our reactants, our products. Now, when we do a chemical reaction, the first thing that we do is that we break all of the bonds. Okay, so this is bond breaking. And then, after that, we make all of the bonds. Bond making. All right, and you can see that because the bond breaking is endothermic, that part of the process is going up. Because bond making is exothermic, that part of the process is going down. However, in this one, overall, it is exothermic, but we'll come to that in a bit. Okay, so I've gone through that quite quickly. You might want to pause it now. You might want to go back through and just make sure that you understand everything that I've said. Because now we're going to move on to some examples, some more examples. Okay. So you will quite often be given a table that looks something like this. So you have the bond, and then you have the bond energy. So we were just talking about chlorine bonds, and you can see here that the bond energy is 243. And that means if I break 1 mole, I need 243 kilojoules. And if I make 1 mole, I produce 243 kilojoules. So now let's use this table to work out the bond energies for a few molecules. Okay, so let's do number 1, H2. Let's start nice and easy. So H2 looks like this. What is the total bond energies in that molecule? Well, I need to look in my table. HH, 436. So this is 436. So altogether it's 436 kilojoules per mole. All right. At this point you might be thinking, well, this is fantastic. This is really easy. It does get a little bit more tricky. So let's think about something slightly different. H2O. Okay, now you know H2O looks like this. HOH. So now we've got more than one bond. So we need to be able to add up the energies of all of the bonds in a molecule. All right, because if I want to break all of the bonds, I need to break this bond and this bond. So this is an HO bond, and this is also an HO bond. If I look in my table, HO is here, 464. So this is 464, and this is 464. So the total energy needed to break all the bonds there is 464 plus 464, which is 928 kilojoules per mole. So if I was to break all of the bonds in water, I would need 928 kilojoules per mole. If I was to make all of the bonds in water, I would release 928 kilojoules per mole. Okay, let's do a slightly more difficult one. CH4, methane. Methane looks like this. CH. So it looks a bit more complicated, but all 4 bonds, 1, 2, 3, 4, are the same. They're all CH bonds. So I go to my table, and I have CH is 413. So this bond is 413, this bond is 413, this bond is 413, and this bond is 413. So if I add those up, so that's 4 times 413, which is 1652 kilojoules per mole. Okay, so I'd like you to now have a go at a few of these. So here are 4 more for you to do: NH3, O2, CO2, and CH3, CH2, OH. And I've been nice and I've given you the structure of all of them. Okay, so use the values in the table, which I've sent you out in the task as well, to work out the total bond energies in those 4 molecules. Off you go. Okay, so the first one, we should have NH is 391, so this is 391, this is 391, and this is 391. So the total energy is 3 times 391, which is 1173 kilojoules per mole. Next, O2. Okay, so here you need to be a little bit careful because actually for oxygen it's okay because it only gives you one type of oxygen bond, but you'll notice that for things like CO there are 2 types, and for CC there are 2 types. You need to be careful for that. But for oxygen it's just 498. So that's 498. So you should have 498 kilojoules per mole. CO2. All right, so here you need to choose this one because if it's a double bond, it's 805, and if it's a single bond, it's 358, and we're using double bonds. Okay, and it should be fairly obvious to you that the double bond would have a higher bond energy because the double bond is stronger, therefore it requires more energy to break. So I've got 805, 805, so it's 2 times 805, which is 1610 kilojoules per mole. And the last one. Okay, hopefully you all had a go at this one. So my CH bond is 413. So this is 413, 413, 413, 413, 413. My CC bond is 347, 347. My CO bond is 358. And my OH bond is 464. Okay, so when you're doing this, give yourself loads of space. Don't worry about using up lots of space. In an exam, they'd give you loads of space to do this kind of question. So, you know, draw it nice and big so you can see clearly what you're doing. All right, so then I just add all these up. Okay, so I've got 1, 2, 3, 4, 5 times 413, and then I've got, so I've used that one, 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 plus 347, that's that one, plus 358, that's that one, plus 464 is that one. And if I add all of those up, I get 5 times 413, plus 347, plus 358, plus 464 gives me 3234 kilojoules per mole. So to break all of the bonds in this is ethanol, this is alcohol, the alcohol that you get in your beer and your wine. To break all the bonds in there, if I had 1 mole, it would take 3234 kilojoules. Okay. Now, the biggest risk for doing this kind of question is if you don't lay it out nice and big and nice and neat and do it systematically, you're going to miss one of these. Okay, so it's quite common for people when they do this to think, oh, okay, well, I know that there's 5 CH bonds and there's a CO bond, but then they'll forget the CC bond. All right, but if you write them all out and tick them off as you do them, then you won't miss any. Okay, so in the next video, we're going to use this discussion of bond energies to now go ahead and work out energy changes in reactions. See you there.